Okay, let's jump right in. Large, multimodal models, VLMs, you see them everywhere now.
Yeah, they're doing some pretty amazing things. Describing images, understanding charts, even interacting with software.
Things that felt like pure science fiction just, I don't know, a few years back.
Absolutely.
Yeah.
The way they blend vision and language it's really powerful. But there's a patch with a lot of the top tier ones.
Right. They're proprietary, closed source, so the data they trained on, the actual code, the model weights themselves, it's all kept under wraps.
Exactly. And if you're a researcher trying to figure out how these things really work, or maybe reproduce a result or just build on it, well, that's a huge problem.
Yeah, it really slows down the whole scientific process, doesn't it? How can you stand on the shoulders of giants if the giants won't show you their feet?
Precisely. You end up with these black boxes, and even some models that claim to be open weight might still be using data that was generated by those closed models.
Oh, right. So they're kind of like distillations, copies almost, not built independently from the ground up.
That's a good way to put it. They're not truly foundational in the same way.
Which brings us nicely to the project we're talking about today, Molmo and PixMo. They're tackling this exact issue.
Yeah, their whole mission really is to build genuinely state-of-the-art VLMs using only open weights and open data.
And the key phrase there is from scratch. No leaning on annotations or data churned out by proprietary VLMs.
It's a significant academic contribution because it aims to give the research community a high-performance baseline that's completely transparent, something anyone can examine, use, and build upon.
And that's what we're going to dig into today. We want to unpack the academic innovations in the paper behind Molmo and PixMo. Like, how did they get such strong results using only open resources? We'll look closely at their novel data approach and some clever training tricks.
Okay, so let's start with that core idea, openness and building from scratch. Why was that so central for them?
Well, fundamentally, it's about enabling scientific progress. If the best models are hidden, you can't really understand the principles, right? You can't easily test new ideas. You can't verify claims.
Yeah, it hampers reproducibility and genuine understanding.
Exactly. The field needs ways to build really good VLMs without depending on these closed systems or their derivatives.
Yeah.
They wanted to carve out a truly open path.
And so they introduced Molmo, that's the model family, and PixMo, which is the big suite of training data they created.
Right.
And they specifically point out that for certain setups, like when they pair Molmo with the Metaclip vision encoder and the Olmo language model, both of which are also open, then everything is open. The models, the data, every component, fully transparent.
Which is huge for anyone wanting to replicate their work or just tinker with it. It lowers the barrier significantly.
Absolutely. So let's talk about the data, because PixMo is a really big piece of this. It's not just a data set. It's a whole suite designed very intentionally. 7 data sets in total, a mix of human annotated stuff and synthetically generated data. But the critical thing, again, is none of it uses outputs from proprietary VLMs for the labels or annotations.
Let's start with the human annotated ones, PixMo-Cap. That's their pre-training data set. What's special about it?
The main thing is the quality and density of the captions. They didn't just scrape short, potentially noisy captions from the web.
Right, like alt text or something.
Exactly. Instead, they paid human annotators and gave them specific prompts for each image. Things like,
What?
Like, list all the objects and count them, or describe subtle details, or what does the text in the image say?
Ah, okay. So really forcing the annotators to look closely and provide detailed information.
Precisely. It results in these really rich, comprehensive descriptions, far more detailed than typical captions. And the idea is that training on this dense signal helps the model build a much stronger foundational understanding of the image content right from the start. They collected this for about 712,000 images.
That makes sense. Better input, better initial learning, and then there's PixMo points.
Yeah, this one's for fine-tuning, and it's pretty innovative. It's designed to teach the model several things. How to point to objects you ask about, how to count by pointing to each item sequentially.
Oh, interesting. Like showing its work visually.
Kind of, yeah. And also using pointing as part of a visual explanation. So for annotation, humans would identify an object, describe it, and then physically point to every single instance of it in the image.
Wow, that sounds intensive.
It is. For counting, they'd point to the first, say 1, point to the second, say 2, and so on. This created 2.3 million question point pairs, really grounding the language in specific spatial locations.
Okay, that directly teaches spatial reasoning and counting in a very explicit way. What about the synthetic data? You said they got creative there.
Yeah, PixMoDocs is a great example. Instead of finding document images and asking a VLM to make up questions, they did something different. They used a text-only LLM.
Like Claude or something.
Yeah, like Claude 3.5 Sonnet, they mentioned. They used it to generate code that describes the structure and content of a document. Like, here's a table with these columns, here's a bar chart with this data.
Wait, code, not an image.
Exactly. Code representing the document's logic. Then they used another LLM, maybe a smaller one like GPT-4o Mini, to generate question-answer pairs based only on that code, not an image.
Huh. That's clever.
It is. They generated 2.3 million QA pairs for document, understanding this way. Things about charts, tables, layouts, without ever needing a real document image or a VLM to read it during data creation. Super resource efficient.
That completely bypasses the need for visual interpretation at the data generation stage. Very smart. What about PixMo clocks?
For that one, they generated synthetic images of clocks. They used different watch bodies, different faces, and just programmatically set them to random times.
Just straightforward synthetic images.
Pretty much, yeah. But realistic variations. And the impact was actually quite dramatic.
Oh, yeah. How so?
Well, Molmo, trained on the synthetic data, became incredibly good at reading clocks, state-of-the-art, in fact. It significantly outperformed other VLMs, even proprietary ones, and even on real-world clock images it hadn't seen.
Wow. So high-quality targeted synthetic data can really work wonders for specific skills.
It really demonstrates that. Careful generation can train skills that even massive general models struggle with.
And they had a few others too, right? Like PixMo Ask Model Anything for general Q&A and PixMo Count for tougher counting tasks.
Ask Model Anything used diverse real-world QA pairs, and Count was built using object detector outputs that humans then verified, making it a pretty challenging counting benchmark.
Yeah.
So yeah, it's a really well-thought-out suite, all built openly.
Okay, so the data is clearly a huge innovation, but they also mentioned some tweaks to the model architecture and the training recipe itself.
They did. On the architecture side, one key thing is how they handle images, especially different sizes and fine details. They use a multi-crop strategy, which isn't new in itself.
Right, chopping the image into pieces.
Yeah, but they introduced what they call a novel overlapping crop design.
Overlapping? How does that work?
Basically, when they take patches, especially the central ones, they make sure each patch includes a bit of the area from its neighbors. There's overlap.
Ah, okay. And why does that help?
They argue it's crucial for tasks needing fine-grained understanding. Think about reading small text, OCR. You need context from adjacent letters. Or for generating those really detailed captions for PixMoCap, where subtle features might cross patch boundaries. It helps maintain local context.
Gotcha. So the model doesn't lose track of what's happening right next to the bit it's focusing on.
Exactly. And they sequence these visual tokens, a low-res overview first, then the high-res crops in a specific way for the language model.
Okay. And what about the training process? Any clever tricks there?
A few interesting ones. First, they found they could simplify things. Often people have a separate stage just to train the connector part that links the vision and language components, often using kind of noisy web data.
Right, like a Q former or something similar.
Precisely. They found that because their PixMoCap pre-training data was so high quality and dense, they could actually skip that separate connector tuning stage.
Really? How?
They just used a slightly higher learning rate for those connector layers early on during the main pre-training. It worked just as well, simplifying the whole pipeline. Makes it more efficient, easier to reproduce.
Nice. Less complexity is always good. And what's this text-only dropout thing? That sounds unusual.
It is pretty unique. Dropout is standard. It randomly ignores some inputs during training to prevent overfitting. But here, during the caption generation pre-training, they only applied dropout to the text tokens, not the image tokens.
Huh. Why only the text?
Their hypothesis, backed up by experiments where they removed it, is that it forces the model to rely more on the actual visual information from the image, rather than just leaning on language patterns or biases it learned from the base LLM.
So it makes the model look harder at the picture instead of just guessing based on typical word sequences.
Exactly. They suggest it helps reduce hallucinations, generating plausible-sounding text that doesn't match the image and leads to better visual grounding, which helps downstream. Kind of like making it a better visual learner by partially blinding the language input sometimes.
That's a really interesting idea. Anything else on the training side?
They also found that adding a length hint during the PixMoCap pre-training helped a lot.
A length hint, like
Yeah.
telling it how long the caption should be.
Sort of, yeah.
Yeah.
Even a slightly noisy hint about the target caption length significantly improved not just the caption quality itself, but also performance on other downstream tasks. It suggests that learning to generate detailed output while also considering its length as just a better pre-training goal overall.
Okay. And there was one last thing. A fix for gradient normalization. Sounds technical.
It is a bit technical, yeah,
Yeah.
but important for large-scale training. When you train across many machines, you normalize gradients to keep things stable. They found a subtle issue in a standard library they used that could penalize examples with very short answers, like just one word. By changing how the normalization was averaged across all machines, instead of just locally, they fixed this bias. They said it boosted captioning performance by maybe half a point to a full point.
So even small implementation details matter at this scale.
Definitely. It shows the level of care needed.
Okay, so we have this impressive PixMo data suite and these clever training innovations. How did they actually check if it all worked? Did Molmo perform well, especially against the proprietary models they aimed to provide an alternative to?
They evaluated it thoroughly. They used a bunch of standard academic benchmarks, VQA v2.0 for question answering, ChartQA, DocQA for documents, various counting tests, the usual suspects.
Right.
But they also did human evaluations.
Oh, like asking people which output is better.
Exactly. Pairwise comparisons, kind of like Chatbot Arena, if you've seen that.
Yeah.
Humans compare Molmo's output to another model's side by side and choose the better one. This lets them generate an ELO ranking, like in chess, to see how Molmo stacks up relatively, including against closed models based on human preference.
What were the results? Did the open approach hold up?
It really did. Molmo hit state-of-the-art on several key tasks, counting, for example.
Which they linked back to the PixMo points data?
Directly. That and a specific technique they used where the model does a kind of chain of thought, explicitly pointing to objects as it counts them, showing its work visually.
That visual grounding seems powerful for counting reliability.
It appears so. And clock reading, remember the synthetic PixMo clocks data?
Yeah, dramatic improvement, you said.
Huge improvement over other models, thanks to that data. Their pointing ability, tested on a new benchmark, was also superior, again credited to PixMo points.
What about the dense captioning? That seems central to their pre-training philosophy.
They actually developed their own metric for that, called CAP-F1, to measure the quality, accuracy, and completeness of the detailed captions. They used it internally to guide development.
Okay.
And they found a strong correlation. Models that got better at this dense captioning metric also got better across the board on lots of other benchmarks.
So getting really good at describing everything in detail was a good proxy for overall VLM smarts.
It seems that way, yeah. There are ablation studies where they took out specific innovations like the overlapping crops or the text-only dropout, confirmed that each of these ideas did contribute positively.
And what about the vision encoder? Did they need a proprietary one?
That was a key. Finding the fully open Metaclip vision encoder performed just about as well as closed proprietary alternatives in their setup.
Which is a massive win for the open science goal, right? Proving you don't necessarily need the closed components.
Exactly. And that really speaks to the bigger picture here. This whole project, Molmo and PixMo, it's more than just one model or data set. It's a statement about open science in VLM research.
Yeah, they've shown it's actually possible to build top-tier VLMs using completely open components and open data without resorting to proprietary models or data distilled from them.
Which is huge. It gives researchers everywhere the tools, the knowledge, the data, the models to push the field forward more transparently and reproducibly. It removes that dependency on closed systems.
It really levels the playing field for experimentation and innovation.
It lets the whole community build on a common open foundation.
So wrapping up our deep dives then, we looked at the really unique PixMo data, those dense human captions, the detailed pointing data, the cleverly made synthetic docs and clocks, all created without proprietary VLM help.
And the smart training techniques, the overlapping crops for images, that text-only dropout idea, using length conditioning, simplifying the training pipeline, even that gradient fix.
Right. And the result is Molmo, a family of models built openly that are genuinely competitive and sometimes even better than proprietary systems on a range of tasks.
That's a really strong proof of concept for fully open approaches in this complex space.
It absolutely is. And maybe here's a final thought for you, the listener, to chew on. Think about that finding, that getting a model really, really good at generating dense, detailed captions describing almost everything it sees was such a strong indicator of its ability on all sorts of other visual tasks. What might that imply about the core skills needed for general visual intelligence? Is that meticulous descriptive ability somehow fundamental, something to ponder as you encounter these models out in the wild?